Here's problem 3835. A diffraction grating with 4,000 lines per centimeter is illuminated by light from the sun. The solar spectrum is spread out on a white wall across the room. At what angle from the center line is blue light, 400 nanometers? At what angle from the center line does red light, 650 nanometers, appear? For a diffraction grating, we have in general that the line spacing d sine theta is equal to m lambda for constructive interference. So, if our number of lines per distance is 4,000 lines per centimeter, our distance between lines is going to be 1 over this, inverse of this. In other words, we're going to have 1 centimeter, 0.01 meters, for 4,000 lines. And that is going to give us a spacing between lines of 2.5 times 10 to the minus 6 meters. So that is our line spacing, 2.5 times 10 to the minus 6 for this diffraction grating. So, in general, from this equation here, our theta is going to be equal to the inverse sine of m lambda divided by d. But m is going to be 1 in this case, because we're just going to the maxima, first maxima. So this is going to be equal to the inverse sine of the wavelength divided by d. Sounds good. So for blue light, this is going to be the inverse sine of the wavelength, 400 nanometers, over d, 2.5 times 10 to the minus 6, and sine inverse of that is going to give us 9.20 degrees. So that is the angle to the blue light. And for the red light, I don't have a red color. Let's see. Nope. So we'll go closest thing. For red light, we have inverse sine of the wavelength, 650 nanometers, over the same spacing, 2.5 times 10 to the minus 6. And that is equal to 15.1 degrees. So we will see a spectrum. We'll see blue at 9.2 degrees, going through the full visible spectrum, and red at 15.1 degrees for the maximum lines.